the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact. If you are ready, let's proceed.
Okay, are you going to give some words?
Yes, I'll do a short introduction.
So, I'm ready to go.
Okay, good. So it's a great pleasure to introduce our speaker today, Dave Nowak. So today's seminar is sponsored by his company, Dewberry. So Dave is a senior project scientist at Dewberry. His focus is on GHG emissions inventories and carbon accounting, and helping to build Dewberry's sustainability practice. Dave has over 15 years of experience in the sustainability space. Prior to joining Dewberry, he worked in the Office of Sustainability at the Port Authority of New York and New Jersey on various projects, including energy procurement, GHG accounting, and strategic planning for emissions reductions. He has a Bachelor of Arts in both environmental science and economics from Rice University. And he also has a Master of Science in Sustainability and an MBA as well from the University of Michigan. He's also a lead AP and ENVSP. So today, Dave will talk on demystifying greenhouse gas emissions, a practical guide to carbon accounting. Welcome, Dave.
Thank you. It's great to be here. Welcome, everybody. Sorry, 1 second here. Yeah, it's really great to be here. I've been looking forward to this for a while, and I'm glad we have such a good turnout. Yes, we are going to be talking about demystifying greenhouse gas inventories with a practical guide to carbon accounting. Just a little bit about me. Professor Dibbs already gave. Yeah, I'm a ENV SP and a lead AP. If you're familiar with lead, Envision ENV is the same thing except for infrastructure projects. Yeah, I went to Rice University for my undergraduate degree, did environmental science and economics, and worked for a bit, continued with that theme. I went to the University of Michigan, where I got an MBA and a master's in sustainable systems from the environmental school. So a very similar program to what y'all have at Stevens. And I had the pleasure of being at Stevens for the program's commencement ceremony to hand out an award on behalf of Dewberry. And I have to say, I was really impressed with all the students and faculty that I met, and especially the capstone projects. Like, y'all are doing great work. I think Stevens is a great school and it's a great program, and I've been trying to tell everybody about it. It's like, yo, it's Stevens, you know, you should check them out. And yes, I'm a senior project scientist in the sustainability group, small but mighty, at Dewberry. Just a little bit about Dewberry. It's a full service engineering firm, about 2,500 employees, which is big, but not as big as some of the other behemoths out there. We're headquartered in Fairfax, Virginia, and we have a strong presence in the Northeast. We have 3 offices in New Jersey, Parsippany, Mount Laurel, and Bloomfield, and also in New York City. And for any students out there, you know, we're always looking for new hires and interns. So please keep us in mind. If you have any questions about Dewberry or just careers in general, please connect with me on LinkedIn. I'm always happy to chat. So what we're going to go over today is just a quick introduction and background. Then we're going to talk about why is this important? Like, why do we care about greenhouse gas emissions and doing inventories and accounting for them? And I understand that people may come in with different backgrounds on this. You may be an expert, or maybe you don't know much. Maybe you know some, but you're curious. So I try to make this presentation to appeal to everybody. And even if you're an expert, I try to sprinkle in some tidbits that you might find interesting. So we'll go over a greenhouse gas primer, just the basic science. And then we'll get into how to conduct an inventory, how to set one up, and how to calculate the emissions as part of that. And then talk about next steps. Great, you have an inventory. What do you do with it? And then I'm going to tell a story about refrigerants. So get excited for that one. And then I'll share a few closing thoughts. So I want to start with the terms global warming and climate change. And those are used often interchangeably, which I think is fair. They talk about the same subjects, but they're slightly different. Is global warming is the average temperature of the Earth is increasing. And climate change is the effects of global warming. What the increase in average temperatures, what does that mean? And it comes about in extreme changes in climate and weather. Some of the graphs on the right is, the top graph is the temperature for this year, average global temperature for 2023, compared to the temperatures of past decades. You can see we're well above what we've seen in the past. And in fact, the graphic below, September 2023 was the warmest month on Earth on record. You see all the dark red, that's record warmest temperatures for that month. So this is real, it's happening, and it's happening now. And getting into why this is so important. So this graph is very different. This goes back, 800,000 years, getting data about CO2 concentrations in the atmosphere. And you go back that far, you're looking at ice core data. There's a lot of methodology that goes into it. But this graph is a few years old. So I had to update it because we are now at 424 parts per million of CO2 in the atmosphere. So we've broken this graph from like 5 years ago. And in fact, I used this same graphic maybe about a year ago or 8 months or so. And I had to update it again because we went up even further from 420 to 424. So again, you can see we are in unprecedented times and feeling unprecedented effects. These are one of my favorite graphics. So these are called climate stripes. If you go to showyourstripes.info, you can look these up. So this specific one, I'll walk you through this, is temperature change in New Jersey since 1895. And the darker blue colors indicate it was colder than average, and the darker red numbers mean it's warmer than average. So you can look back, you can see, there are some cold years, there are some warm years here and there, but then you look recently and you can see it's basically all dark red. And those are the trends that we're seeing. And I highly recommend to check out this site. You can change states or countries and you can compare the trends across different locations, but it's a really beautiful representation of data. And we talk a lot about the impacts of global warming and climate change. So the primary impacts are sea level rise. There'll be extreme temperatures, both warm and cold, and extreme changes in precipitation. What I think is interesting is, those are the primary three, but there are secondary impacts. There's increased wildfires. As the water heats up, coral and coral reefs gets bleached and the reefs die. The ocean becomes more acidic, which also affects those ecosystems. Another one is disease vectors, and this is something we're seeing now where we live, where the warmer weather, ticks have a longer season. They're able to stay active and kind of move further north, and that brings disease with it. Another one that I really like is that I just heard this term recently is the impact of a false spring. So let's say it's February and you get a huge warm spell, which may sound nice after months of winter, but that confuses the flora and fauna, where they think like, hey, spring is here, great. So the trees will start to bud out, animals will start to migrate, but then if it gets cold again, like it's supposed to normally, then they run into a lot of trouble. So, there's so many secondary impacts that you can talk about. And actually, let's think about, I mentioned that this is happening now, so let's think about what's happened in the past year. In Buffalo last year, there was a tragic snowstorm around Christmas, I want to say, and they ended up with over 7 feet of snow, which is a sight to behold. And you may wonder, well, how is that related to climate change and global warming? Well, Buffalo gets hit by lake effect snow. It's right on the shore of Lake Erie. And the way lake effect snow works is when a really cold air mass moves across a warm body of water, in this case, the lake. And at this point, it was warmer than average at a very high temperature. It wasn't covered in ice yet. And the warmer the water is, the more moisture gets picked up in the atmosphere. That's how you end up with 7 feet of snow. And I think, we all remember over the summer with the wildfire smoke coming from wildfires in Quebec. That's an impact that is happening thousands of miles away, but we were feeling it here in the city. And then just a few weeks ago, New York City had, I think it was the rainiest day on record. There was incredible flooding. This picture down here is this is actually on the block that I live on in Brooklyn. So my end of the block was fine. I'm fine. Thank you for asking. But it's just the other end of the block, it has kind of a dip, and the infrastructure isn't there to handle this type of flooding. And that leads into a whole other discussion about the resiliency of infrastructure. Like, we could have several whole presentations on that. But these impacts are happening now, and we are feeling them. So let's go over some basic science with the greenhouse effect, which is essentially sunlight comes in to the Earth's atmosphere, and it usually either gets absorbed by the Earth or reflected away. Sometimes, gets bounced back out into space. But greenhouse gases trap that heat, and that's how the temperature rises. That's how you end up with global warming. And we often talk about carbon dioxide, or CO2, as sort of a placeholder for greenhouse gases. Well, there's many greenhouse gases aside from carbon dioxide. So you can see the table down to the left. Those are the main greenhouse gases. And you'll notice the far right column, there's a global warming potential, because not all gases are created equal. Depending on the life in the atmosphere and the chemistry and how they react, they can have a profound effect, more so than just carbon dioxide. For example, 1 molecule of methane is worth 21 molecules of carbon dioxide, okay? And nitrous oxide, 300. And then you'll see these at the bottom 3 rows, these very complicated chemical names have global warming potential into the tens of thousands. So those are refrigerants, and I promise we'll get there. But the way to kind of summarize all this is that you look at the global warming potential of each gas, and you convert it into a carbon dioxide equivalent, or CO2e. Okay, And emissions are measured by mass. So you typically say metric tons of CO2e. You can use other things, you can use kilograms or pounds, but at the inventory level, it's typically metric tons. And to be clear, an inventory is emissions over a period of time, which almost always is a year. So you end up with this unit of metric tons of CO2 equivalents per year. So that's kind of the default unit that we're talking about. Okay, so inventory basics, how to do an inventory. So step one is to set your boundary. Okay, what does your organization do? What activities is it responsible for? Okay, and you establish operational control. So it's like what you do and what you can control. For example, let's say you have a widget factory and you make widgets and you go sell them in your widget stores. You know, those are things that you can control. You can make your factory energy efficient, or your stores that way, or find new ways of transporting your widgets to and from. But let's say you don't have your own stores, you sell your widgets to, I don't know, Target. Well, you can't quite control what Target does in terms of their activities or energy efficiencies. So operational control is really important, and that's called scope 1 and scope 2 emissions. Okay, and to define those a bit further, scope 1 is on-site combustion. So simply put, think about a smokestack or a tailpipe, where it's on-site and the emissions are actually coming out of that location. So some examples are stationary combustion. So if you have, you're using natural gas or some sort of boiler in your facility. Mobile combustion is also considered on-site. I mean, think of a tailpipe. So that could be vehicles that you're driving, or if you're using generators, for example. And then it also includes fugitive emissions, which again gets into those funky chemicals we saw before, and refrigerants and fire suppression and other manufacturing processes. Okay, so that's scope 1, on-site combustion. Scope 2 is called indirect emissions, and it's real simple. It's basically electricity. Okay, so you're using the electricity in your place of business or your home or your widget factory, but the emissions are actually coming out somewhere else, you know, wherever the power plant is. So those are called indirect emissions. And now this is where things get kind of complicated. But luckily, it's all bucketed into scope 3, value chain emissions, which is basically everything else. So it's areas that you do not have direct control over. So, you know, you can't tell Target how to manage their stores to reduce emissions. It could be a lot of things. It could be business travel or employee commuting, disposal of products as well. And these are really challenging to calculate because you don't necessarily have the data or the insight to take a close look at them. And you know, it's important to note not all are applicable or relevant. You know, if you're not selling a product, there's no what happens to the product at the end of life. You know, so you kind of pick and choose what is applicable to you. And there's overlap. So my scope 3 can be your scope 1. You know, so my scope 3, like Target, whatever, you know, I can't control them, but Target can control itself. So the emissions coming from their stores are like their scope 1 and 2. Whereas for me, they're scope 3. And it's important to note that scope 3 is usually orders of magnitude more than your operational control emissions in scope 1 and 2. So prior to joining Dewberry about a year ago, I was at the Port Authority of New York and New Jersey. So which is, you know, massive. The inventory is incredibly complicated. You know, they're doing huge facilities, airplanes, traffic, all sorts of things. And their operational control was 225,000, again, metric tons of CO2e. Scope 3 emissions was nearly 5 million, okay? And a lot of that comes from just aircraft taking off and landing at JFK. There's a whole methodology for that. But yeah, so scope 3 is typically a lot larger. It's harder to calculate and it's harder to address as well. So there's a simple methodology in terms of calculating emissions, and I'll run through some examples here. So you start with your activity data, like the data that you collect. You run it through a tool or a methodology, and it calculates emissions. I mean, everything basically follows that same structure. For example, scope 1, operation control on-site combustion, so natural gas. Your natural gas consumption probably comes in a unit like therms, okay? You can look up the conversion factor. So 5.31 kilograms of CO2 per therm. So you multiply the consumption out by that conversion factor. There you go. You have your emissions. Let's talk about construction equipment. Again, this is scope 1. The operational data here may be a bit more complicated. Maybe gallons of fuel used or hours operated by this excavator or bulldozer, or you may have to have information about the engine types and age that you're using. But there's a tool for that, and it comes from the EPA. The EPA has a lot of tools out there. In this case, this one is called non-road, and you can put in the different inputs and you'll get your emissions at the end of it. Scope 3, scope 3 is challenging, but customer traffic, vehicle miles traveled. So some of our clients that I'm working with at Dewberry are regional transportation agencies, and their biggest source of emissions is if they, for example, have a highway. There's cars, their customers driving up and down the highway, and they're all releasing emissions. But there's a tool for that as well called EPA Moves, where you can put in vehicle miles traveled, they call it. And this tool is really robust. It was actually just updated a few months ago, so we've been trying to figure that out. It accounts for a lot of things, even like weather and climate. I think it gets into like tire wear. It calculates other things than GHG, but these are really impressive, robust tools that can help you get your emissions. Okay, so this is my favorite, is scope 2 electricity for indirect emissions. Okay, the tool here is called eGrid, and again, this comes from the EPA. So eGrid is location-based electricity emissions based on the electrical grid. So if you look at the map over there, yeah, there's the electricity grid in the nation, but it's a little more complicated than that. There's sort of regional subgrids that, they're all connected, but it's not like one big mesh of a network. And these grids are basically where your electrons come from. So if I, plug into an outlet, my electrons are going to come from, one of these specific regions, depending on where I'm in. And it's really impressive because these emissions come from actual power plants, and the EPA collects data on how often they run, like really detailed technical data, the amount of fuel that they consumed, and then they roll it all up into one number that you can use to calculate emissions. So what's interesting is I highlighted RFCE, which is the grid for New Jersey there. And you can see the number, it's 655. But you see that there's a range there. So New Jersey is kind of on the lower side because I believe there's a lot of natural gas and like nuclear power there, things that have lower emissions. But for example, if you go to the Midwest where it's dark blue, that's a lot more coal. So you see the emissions factor is a lot higher. Conversely, if you go to the Northwest or Northeast or even upstate New York, there's a lot more renewables there. And that especially includes hydroelectric power. A lot of the Northeast actually gets their power from Quebec that has a lot of excess hydro capacity. And one of the projects is, this is pretty crazy, that they basically run a wire down Lake Champlain and like down the Hudson, like buried in the riverbank, and plug it in directly into Queens to bring in renewable emissions-free energy to New York City. And so as more renewables come online, such as that, or offshore wind is a huge effort, especially in the Northeast, these e-grid factors will decline. So that's why, you know, you talk about electric vehicles, like, oh, powering it with like coal power. Yeah, that's not the best. But as more renewables come online, these emissions numbers, you know, the emissions coming from your vehicle will start to go down. So, and again, you know, outside of e-grid, what do? You take your electricity consumption and multiply it by the factor and you get emissions. But you got to be careful though, because if you look down at that table, watch your units, right? This is good scientific practice. You start with kilowatt hours and the conversion factor is pounds per megawatt hours. So you have to make sure to convert that into metric tons of CO2. So some of the best practices about an inventory, you know, like we discussed, you have to establish your boundary clearly. Like, what do you do? What do you have control over? It's easy to kind of have scope creep where you're looking at other things. No, you have to be very specific of this is ours, this is related to us, but we can't control it. And you have to decide what is important. There could be, for example, you know, emergency generators, those are a source of emissions, but it's typically very small. So you kind of have to pick and choose, given how difficult it can be to get data, you know, what's important, or what things can you kind of let slide or make more basic assumptions about. And this, I think, is the most important thing, is data quality and format is critical. Like, for example, at the Port Authority, we had this energy management system that had all of the electricity consumption for all like hundreds of accounts by month, and that was great. But if we didn't have that and we had to go through hundreds of accounts with like paper invoices, that can take a lot of time and that's very prone to error. So it's really important to look at the quality of the data that you have and understand its limitations and the sources that it come from. Also, you can make educated assumptions too. Like, yes, there's a greenhouse gas protocol that has rules to follow, but you can follow those rules and make certain assumptions. For example, so I actually did Dewberry's own inventory, which was a really exciting project. However, in collecting the utility data for electricity and natural gas, you know, some of the offices that we leased, we didn't have that information. So again, we found a tool and methodology where it looked at the average square footage of an office. This is an online database from the Department of Energy, but it gives you that number and then you can, okay, we have this much square footage. This is how much electricity we use, probably. And you can convert that into emissions. There's always assumptions and tools that you can make, but you have to find the right one. And it's really important to document and be transparent. Think about this as, well, we call it greenhouse gas accounting. So you have to follow like accounting procedures and you have to document where this number is coming from. Where is the data from? You know, what, for example, QC process did you go through? What assumptions did you make? Because essentially what you want is for someone to face with the same data to be able to come in and do the exact same inventory that you did. Which, and you can actually do your own inventory if you'd like to. So, you probably pay utility bills, most likely. So how much natural gas do you use? That's your scope 1 emissions. How much electricity? That's scope 2. And you can use the same tools that I just talked about to get your emissions. Big one you have to look at is travel. So this table shows the emissions rates of various different transportation modes. So you can see passenger car and light duty truck, it's not very good. But if you're taking transit rail, like the subway or the path, let's say, the emissions factor is a lot lower. And if you're using your own vehicle, like how many miles do you drive it each year? What's your vehicle's fuel efficiency? And this is important, but don't forget about vacations. Air travel is very carbon intensive, and you can rack up miles pretty fast that way. So it's important to look at your air travel emissions. And this is especially true when we're looking at Dewberry, and there's a lot of air travel for business travel. Those emissions add up pretty quickly. And for your own scope 3 value chain emissions, these are hard to calculate, but be creative. Maybe you order a lot from Amazon and you get things delivered. Maybe you get it in all the separate boxes because you need it immediately. But maybe you can combine that into one shipment. That would save emissions. So there's a lot to think about, and let your imagination run wild. Here's another really interesting tool. It's the EPA's GHG equivalences calculator. Because right now, you're right, we're just kind of throwing out numbers. So what do these mean? So the way this tool works is just a real simple website. You can put in your energy data for your electricity bill, kilowatt hours, or you can put in emissions, and then it puts those numbers into context that's easily digestible. So we talk about 1,000 metric tons of CO2e. Well, that's like driving a car, 2.5 million miles, or it's equal to 126 homes energy use just for 1 year. And it gives a lot of these kind of fun conversions that really kind of put things into context, because you can often end up talking about inventories, end up with huge ridiculous numbers, like we talked about the Port Authority's 5 million metric tons of scope 3 emissions. And it's like, well, what does that mean? How can I visualize that? And even then, sometimes the numbers are so large that you kind of need to calculate that again. So, the 2.5 million miles, like how many trips is that to the moon, let's say? There's a lot of ways that you can present the numbers to better communicate your points. So this is a real fun website to kind of play around with. Okay, so you have an inventory. I mean, no one does an inventory for fun unless you're like me or a dork, but you essentially set an inventory to set a goal. Like you say, these are our emissions now, where do we want to go? Do we want to reduce by a specific amount? Do we want to reduce by a percentage? And when do we want to do that? Do we want to be carbon neutral by 2050, or have an interim target of 25% reduction by 2025? The first step is to do that initial inventory and set a baseline. Next is, well, it's really important to identify opportunities and strategies for reduction. So here's a really excellent graph from the city of Toronto. So they have their emissions, and then they have like, here's the projection if we do nothing. And then the lower line is like, okay, here are our targets that we're trying to hit in the future. And then they figure out that gap and they look, okay, here's what we can achieve using these different programs and initiatives. We can get this much from building energy efficiency. Electric vehicles will give us this much. And that's important because you don't quite know where to start until you do an inventory. For example, for Dewberry, in our inventory, we found a lot of our offices don't use natural gas. Like the amount of emissions from natural gas is very small. So, there's not a lot of opportunity there to make significant change. Where we did find there was changes with our fleet vehicles, that we use for business trips or doing field work. So now that's become the opportunity of what if we try to electrify those vehicles? That's where we can make, realistic and effective change. Other things you can do with an inventory is get it third-party verified. So remember, I said it's like accounting. A third-party verification is basically like an audit, where, fortunately, as I'm sure you documented your inventory, are very transparent about what you did. So it's easy for the verifier to come in and like give it the stamp and say, yep, this is good. This is all proper and follows the right protocols. And that's also a step for public reporting. Some of the big ones below are CDP, which is formerly the Carbon Disclosure Project. That's a huge reporting platform. You go there, there's a lot of information that you have to submit, even beyond just an inventory. But they'll give you a grade. You'll say, here's your inventory, here's your goal. Is it achievable? And they'll give you like a letter grade, so you can get an A. So you can go there and look up the grades of nearly any large company in the world. Like almost every corporation is doing this. And it's a good way to compare their sustainability efforts and their progress against each other. Another one is science-based targets. This one is really very technical. But they look at your inventory and your goals and see, is that achievable? Is that realistic? And will that be enough of an improvement to limit global warming by 1.5 degrees Celsius? So it's science-based targets. Like you could throw out, we're going to reduce by X%, and it's like, well, okay, but what are you really talking about? Is that realistic? So that's another third-party reporting platform. And I also like to call carbon dioxide equivalents as kind of a common currency that you can use to communicate internally and externally. And internally, especially where, look at this graph, you're trying to decide, okay, building energy efficiency or electrifying our fleet. Well, you can look at, okay, for this effort, we get this much reduction, but this other effort, we get more of a reduction, and you can compare that to investment, let's say. So it really creates a common currency or a common language between different sustainability strategies, so you can compare and contrast them. I think that's one of the really useful things about carbon accounting and doing inventories. Here's a slide. I just want to touch on this because there's a lot of talk now about embodied carbon and life cycle emissions. Okay, this is related to, but a little different than an inventory. So life cycle emissions are greenhouse gas emissions associated with the manufacture, use, and disposal of a product or service. So you have to consider the entire life cycle and compare apples to apples. So here's this graph. So you'll often hear people say, oh, electric vehicles, they're more energy intensive to make. They require more carbon than an internal combustion engine vehicle, which, if someone says that, you can say, yes, that is true. That is a fact. It is more resource and energy intensive to make an electric vehicle. But where the difference comes in, you can see the electric vehicles, the two columns to the left. Where the difference comes in is the use phase, where as you're driving that vehicle, you're using electricity. If you're driving your internal combustion engine, you're using gas. And that's where the largest source of emissions come from. And if you notice, there's the air bars on the electric vehicles. So that goes back to EGRID, like where are you getting your electricity from? Are you getting it from a region where there's lots of renewables? Your emissions will be a lot lower. If it's not, then less so. There will still be, slightly greater emissions associated with that. But it's important to consider the entire life cycle, especially use. Use phase, I think, is the most critical. And it really allows you to compare apples to apples. Okay, here it is at last, a story about refrigerants. I know you guys were all excited about this. So, because I know that there can be a lot of doom and gloom when talking about global warming and climate change, but this is something that kind of heartens me. So back in the 80s and 90s, one of the big environmental issues was a hole in the ozone layer, especially over Antarctica and the southern hemisphere, that would lead in like more solar radiation, a lot of other effects. But you don't hear about that as much today. In fact, what you hear is that the hole is stabilized and is actually reducing itself. It's naturally regenerating itself. So why is that? Back in 1987, countries of the world got together and passed the Montreal Protocol to phase out CFCs, chlorofluorocarbons, that came from refrigerants or from aerosol cans. So they realized these were the chemicals that were interacting with the ozone layer. So they said like, hey, let's not produce those. So they came up with replacement chemicals, I think generally HCFCs. So those were better for the ozone layer. They weren't perfect. However, you know, the Earth is a complex system. Turns out those are really bad as far as global warming. Like these are the ones with the global warming potential of in the 10,000s down there. So then the world got together again. So like, okay, let's phase out those. Let's use HFCs. And now it's become, okay, we're gonna phase out those and use, honestly, like carbon neutral refrigerants. So, you know, the lesson is the Earth is a complex system. There are always unintended consequences that you might not think about. But it means, I mean, look at this. We work together to solve a global problem. We've done it in the past. My hope is that we can do it again, just to give a little bit of hope. This is yeah, I'm gonna close out on this very basic slide, which as simple as it is, I really like it. So the top, there's mitigation and adaptation. So in the term for climate change and greenhouse gas emissions, mitigation means, okay, let's reduce emissions. Like we need to bring in more renewables, for example. You know, let's take these strategies to reduce our emissions. We do an inventory, we set a goal, now let's take the steps to get there. That's mitigation. Adaptation is, well, let's adapt to the new world that we're living in. We will deal with climate change and sea level rise. Let's build our cities to be able to respond to these extreme weather events. That's adaptation. And for a while, those are kind of opposed to each other, where adaptation would say, look, this isn't realistic, like let's prepare for this new world. And mitigation would say, no, you can't just give up, like we need to do something. And really the time now is become, it's time for both. We need to mitigate emissions and also adapt to this changing world, because we're already feeling the effects. Like it could be a lot worse unless we take action now and mitigate. And I think this dovetails really well with, you know, these other terms that you hear, sustainability and resiliency, where there's lots of fun definitions of sustainability and resiliency. And these terms are often used interchangeably, but they're slightly different. My favorite one, though, is sustainability is protecting the environment from, let's say, infrastructure or people. Resiliency is protecting people from the environment, right? Like, you know, you need resilient stormwater infrastructure so we don't all flood like we did in Brooklyn. And so mitigation and adaptation, in my mind, are very similar to sustainability and resiliency. And they're kind of all related. And again, I think it's the time to have an all of the above approach. Okay, just some closing thoughts. So I was thinking about how I got involved in greenhouse gas accounting and doing inventories. And the answer is I'm not quite sure. I learned about the principles in school, and then when I was working after undergrad for another engineering consulting firm, there was a project that came up involving greenhouse gas emissions, and I basically learned on my own essentially as part of that, like looking at the references and figuring out like, okay, this is how you do electricity, this is how you do refrigerants. And then in grad school I did my capstone project on greenhouse finance, what was it, greenhouse gas emissions in the financial services industry, which we could talk about if you guys have questions on that. And then when I was at the Port Authority, I had a lot of other responsibilities, but they've had a long, robust inventory and emissions process going back to, I think, 2006. Well, there's someone there working on it, and I said, like, hey, I have experience in this. Do you need help? And they're like, yeah, absolutely. And then by the time I left, I was managing the entire inventory process. So I don't know, it kind of happened organically, and it's important to take the opportunities as they come up in your career. And yeah, you never know. My ultimate hope is that maybe this talk might encourage someone else on their own journey. And my second point is that journey will look very different than my career or anybody else's career. The environmental movement, so to speak, broadly, has changed just drastically. I mean, you can go back to the beginning with the first Earth Day and Rachel Carson's Silent Spring and the EPA and all the landmark environmental regulations in the 70s. But even since I started, so when I was doing environmental science and economics, people would say, why are you majoring in those? Like, both of those are opposite things. Like, that's so stupid. I'm like, no, you don't understand. They're inextricably linked. Like, this is how we solve things. And then several years later is questions about like, okay, what is sustainability? Like, what does that mean? That's what organizations and companies were asking. And we sort of kind of had to define that and explain the principles of that and what you can do, because that was the next question. Like, great, we're all about sustainability. What do we do with it? And contrast that to now, where you have ESG, sustainability investing in firms, environmental, social governance. Well, that's become a really hot topic now. And who knows what it's going to be like 5 or 10 or 20 years down the road. But I think it's exciting times. So, all right, that's all that I have. I'm happy to hear any questions or thoughts.